My name's Tony Gibbs. I'm a data warehousing solution architect with Amazon Web Services, and today we're going to be going through best practices on Amazon Redshift. So let's get started here. I always like to ask this one just to kind of get a feel for where you guys are all at. How many people here use Amazon Redshift on a regular basis? Oh, wow. That's awesome. How many of you are evaluating Redshift? You don't actually use it today, but you're maybe looking at it. Okay, this is perfect. This is exactly what I was hoping I'd see. How many people have never used Redshift? You're just interested in it, maybe something of interest? Okay, a couple of you. So this talk is mostly geared for the first, couple people I was asking about. The rest of you, I have tried to make it in such a way that if you're familiar with data warehousing, databases, you should be able to get something from this, enough to at least get you started on Redshift. So let's get started here. We're going to quickly start out. We're going to move through this first part. It's the history and development of Redshift, where it came from, our history, the last 4 years of development that we've done. Then we're going to move into concepts, table design. So some of the concepts are mainly to make you aware of, some of just how we talk about Redshift. Then we'll go through table design. And the next part is best practices on ingestion, and data loading and ELT and that sort of thing. And then we're going to wrap up. The last part will be on cluster sizing. So this one will be fantastic for the few of you guys who are never used Redshift and maybe you're going to give it a try. Or if you're working on a migration or something like that, that section will be good for you. And then we're going to finish with whatever Q&A time is left, and you guys can ask me all sorts of stuff. I will also hang out after the presentation, outside or wherever, and you guys can continue to ask me questions, and I'll stay for as long as you guys continue to, have questions. So let's get moving on with the history of Redshift. Really kind of starts out with Postgres. If you connect to Redshift for the first time, or for all of you guys who have used it, you will notice that it returns back a Postgres connection string. We obviously rewrote the entire storage engine. It's a Columnar storage engine. And we made the system MPP, which is why you can scale it horizontally up to 128 nodes. Then we added a lot of analytics functions, approximate count distinct functions, approximate percentiles, and all these other kinds of functions that you typically use in an analytics data warehouse. We wrapped all of it up in AWS, so this is integration with S3 for backups and restores and loading and all that kind of stuff. KMS for encryption, IAM, which is for authentication and connecting to S3 and such. And it really is the combination of all of these components that make Redshift what it is. We launched Redshift almost 5 years ago. It went GA on Valentine's Day, February 2013. And since that time, we have added a lot of features and functionality. We've really been innovating and adding to the product. We do patches typically on a 2-week cadence. It is a fully managed service, so that means you set a 30-minute maintenance window, and we roll out those patches continuously, security updates, and all of that kind of stuff. And it's not something you really actually have to worry about. Just check the patch notes, and you get some new cool features and such. So let's move on to the concepts and table design. I'm going to just start out with the architecture of Redshift. The top part up here, that's kind of where you connect from, the SQL clients and BI tools. Redshift supports, we actually supply JDBC, ODBC drivers, but it does support the use of also Postgres drivers as well. So if, say, you're wanting to connect from Python, for example, you can use PsychoPG2, which is the Postgres Python driver, and you can connect to Redshift with that. Your connection connects to that top blue box there, which we call the leader node. The leader node does all of the query parsing. It does query coordination and all of that kind of stuff. It also stores this PG catalog. So if you actually are familiar with Postgres, you'll see that the PG catalog in Redshift is intact. Behind the leader node sits up to 128 compute nodes. This example has 3 compute nodes. You can go from 2 to 128 of those. that's where the data actually resides in Redshift, and that's also they're what do all of the heavy processing and heavy lifting of the data. The one thing to take away is that they do everything in parallel, all of them together. And that's something what we call a massively parallel architecture. So every compute node works on a single query all at the same time. These compute nodes also talk directly to S3. So this is typically how you load data in and out of Redshift. We'll go much deeper into that. The backups and restores also go directly from the compute nodes to S3. Earlier this year, we released what we call Amazon Redshift Spectrum. This gives Redshift the ability to query S3 directly. And we do this by provisioning there's actually another layer of compute that sits between. It's an elastic layer, and that's what actually does the querying of S3 and passes the data back up to your Redshift compute nodes, and then obviously up through the leader node and to you. You can also load data through the Spectrum layer, and we'll talk about that in the ingestion section as well. So the first terminology, I already mentioned it, Columnar. Redshift is a columnar data warehouse. So what that means is we store data on disk column by column rather than row by row. And the reason we do this is because the queries that you typically run against a data warehouse, like sums and averages and various other aggregate functions, typically only operate on a subset of the columns. So when you're only querying some of the columns and across millions or billions of rows, a columnar architecture greatly reduces I/O on those sorts of operations. Just to illustrate that, suppose we have this deep dive table, very simple, we only have 4 rows in it, and we have a SQL query which we're going to select the minimum date out of that table. In a row-based database, like say Postgres for example, assuming there's no indexes or anything like that, you would end up having to scan through the entire table to find that minimum date. Whereas in a columnar data warehouse like Redshift, what happens is we only need to read the data for that date, and thus we reduce I/O. The next piece is compression. Compression does 2 things in Redshift. One, it allows you to store significantly more data in your cluster, up to about 4 times more data. It also improves the performance of Redshift as well. And the reason why is we actually reduce I/O. We've stuffed more data into our data blocks, and we're able to read more off disk quickly. There's a lot of CPU, and I/O is still the bottleneck, so that's why it improves performance. We do our best in Redshift to figure out the optimal compression for you. So the first time you load data into a Redshift table, we will try to figure out that compression. We also have a utility or command built into Redshift called analyze compression. That will find the optimal compression for you. Just to quickly give an example of how compression works in Redshift, same table, same data. If we modify the DDL with these encode statements here, that's how compression is applied to Redshift. So we're going to add, Z standard, which was a new compression type we added earlier this year. In the first example, byte, dict, and run length are just a couple of the examples that we have for our encoding or compression types. So the best practices on compression in Redshift, the first is try to apply compression to all tables. If you run the analyze compression command, you may notice sometimes you get raw, which means no compression, for some columns or maybe for all of them. If that's coming back, that's because the table is so small that there's not really a benefit to adding compression to it. So don't be alarmed if you see that. We also have, this is a GitHub link. We have a ton of scripts on GitHub, and you're going to see these links throughout the presentation, but this is the first one. This utility here on GitHub is one that we built and posted that will help you migrate tables that maybe don't have optimal compression in your Redshift cluster, and they'll rewrite the table and copy the data over. That SQL query there, that's one of the PG tables that we've actually added into the PG catalog table, catalog schema, and that would be an example of how you'd find the compression on an existing table. So the next concept to talk about is what we call blocks in Redshift. This is basically how the columns are constructed. They're 1 meg immutable chunks that we store on disk for each column. Every block will have one of 11 different encodings, with one of those encodings being raw, which means uncompressed. When you factor compression in, one of our data blocks can store millions of values. So when you think about that, that means that a single block in Redshift holds the values for millions of rows for that one column. The next concept is zone maps. And this really does relate to blocks, because this, what they are is it's metadata about the blocks. So the main piece of metadata that we have here is we store the minimum and the maximum values within each of those 1 meg blocks. And the reason we do this is when a SQL query comes in, we can check this in-memory data structure and we can prune data out. The next concept is data sorting. This is physically sorting data on disk in Redshift. So this is you essentially picking one or more columns and sorting the table by those. And the point of this is to make the zone maps on the previous slide more effective. That is the primary purpose of a sort key. Typically, they're put on the columns that you're filtering on. So if you have a where clause, or like a predicate essentially, and you're doing, where this date is between these values, for example, that's an example of where you'd want to place your sort key. Obviously, sort keys depend on your query patterns and your business requirements and that sort of thing, but a lot of times it will land on the columns that you primarily are filtering on in your SQL queries. Just to give a quick example of how sorting is done in Redshift, the same table, same data, been already working with. We modify the DDL here, and in this example, I'm adding a sort key to first the date column and then the location. If I were to sort this table now, the data would end up like this, sorted first by the date and then by the location. And the point here is to make the zone maps more effective. To illustrate the two working together, suppose we have 4 data blocks here. We have the zone maps, which are the metadata there, which is held in memory in Redshift. And we have a SQL query where we're just going to basically count the number of records on a certain day. What Redshift is going to do is it's going to check the zone maps first and go, I only need to read these 3 data blocks off disk. I can skip reading this one, which reduces I/O. And that's exactly what the zone maps do. If we take that same table and we sort it by the date, now what happens is the zone maps are in a more optimal condition for this SQL query, and we reduce I/O further. So the main point is that sort keys are primarily making the zone maps more effective. Usually it will end up being on a timestamp, and that's because in data warehousing, you guys end up having some sort of temporal column that you're searching or filtering between. That's not always the case. If you have many columns or more than one column in your sort key, ideally you want to have the lower cardinality columns first. So this might be maybe there was an organization ID and then a timestamp, for example, and that organization ID maybe only had a dozen values. That would be an example of where you would change the order of those and not have your date column first. We do have a couple of GitHub scripts if you have an existing workload that you can run against your Redshift cluster. What these scripts will do is based on the logs in your cluster and what you're typically running queries against those tables on, they will look at that and return back what you're usually filtering on. One thing to make a note of is sort keys on really small tables, they're not really necessary. So if you have a table of, like, say, 10,000 rows, you don't really need to sort it because chances are the table only has one block anyways, and there's not really anything to optimize in the zone maps. The next concept is slices, which is a really important concept in Redshift. So this is how we get parallelism within a Redshift cluster. So every single one of our compute nodes is divvied up into 2, 16, or 32 slices. We store the data physically per slice, and each individual slice will only operate on the data that belongs to it. So again, it's to get parallelism. It's how Redshift gets its parallelism within a single node. So how do we distribute the data amongst these slices? This is what the distribution keys where they come in. The first one is what we call diststyle key. What we're essentially doing when you pick a column, this is what happens, is you pick a column and you assign it when you use this distribution style. What will happen is the value for that row in that column, we hash it, and that hash corresponds to one of the slices in your cluster. And that's where the data ends up landing. The next distribution style we have is even. What even essentially is we're just going to round robin the data for you on your behalf. It's the default choice in Redshift. The last choice is distribution style all. And what that essentially means is we take an entire copy of the table and we write it out onto each node in the cluster. So the whole table exists on every single node. The reason for that is typically dimension tables, small tables that you're joining to, and you're trying to reduce the network broadcast when you do joins on those tables. So I'm going to illustrate how each of these distribution styles work now. I'm going to start out with even, so the same deep dive table I've been talking about this whole night. And we're going to insert these 4 rows into the table. We're going to start out by inserting the first one there, SFO, and it's going to land on the first compute node here on the first slice. The second row, JFK, is going to land on the second slice in that first compute node, the third one, and the fourth one. So it's just round robining the data through the cluster. Pretty simple. So let's pick a key here. Let's use diststyle key in our second example. And I'm picking the location column here, which corresponds to those values SFO, JFK, SFO, and JFK there. So if I take that first row, and maybe it lands here on this slice, and the second row lands on that slice, what's going to happen is SFO is going to hash back to that first slice, and JFK is going to land on that second slice. Makes sense. However, this is an example of a bad distribution in Redshift. Remember I talked about MPP, massive parallel processing? Well, what's going to happen here is if you execute a query against this cluster, your second compute node doesn't have any data in it at all. And it actually does absolutely nothing. And so you have one node doing all of the work. So that's what we call row skew. So let's pick a better column to distribute by. Now I'm going to pick the AID or audience ID here, which looks like a primary key. That first row might end up hashing out to that slice, the second one over there, third one there, and fourth one over there. Now I obviously baked this example, so it worked out perfect. Statistically, if you have a large amount of rows, it will work out fairly well. So that's the idea of how distribution style key works. So let's talk about distribution style all. What we do here is, as each row comes in, we write it to the first slice on each node so that there is an entire copy of it existing on each slice or on each node in the cluster. So that's how dist style all works. So what are the best practices? The best practices are to use distribution style key primarily for optimizing join performance. So this is, if you have 2 tables, for example, which you join, and there's the on clause, and that on clause has the two columns that you're joining on. Ideally, you want to make that the distribution style for both of those tables. The other primary reason for using distribution style key is if you're copying data from one table into another using an insert into and a select from the other table. If those two tables share the same distribution key, you're going to find that that insert is significantly faster as well. Those are the primary reasons for it. Now, there is one thing that you do, I mentioned, obviously the skew. How do you figure that out? That skew, this is the query in the system table, SVV underscore table underscore info, and it's called skew rows. Ideally, that value should be somewhat close to 1. What it means is if we take a look at the slices, and we take the slice with the least amount of data and the slice with the most data, that number is the ratio between those. So ideally, we want it to be something, 1, 1.1, 1.2. Those are totally fine. But once you start getting, up into 2s and 3s, that's a big difference in data, and your query performance will slow down. So that's where you want to check. Distribution style all, that is for optimizing join performance between your tables, usually your fact tables and your dimension tables. And as a rule of thumb, it's safe to pick or to set that distribution style on a table if it has 3 million rows or less. There are cases when it can be more, but as a general rule of thumb, 3 million rows or less is a good number. As long as you're not, there's one other thing, as long as you're also not reading or writing frequently to that table, because obviously a write to that table means every node in the cluster is rewriting the same data. If the two distribution styles above don't apply, key and all, just use distribution style even. Or if you're really not sure, use distribution style even as well. It won't really do the wrong thing. It won't muck performance up. You will get good performance using distribution style even. Think of the other two as ways to optimize and make things better. So this is a sort of a summary plus a few extra points. The first point is to materialize frequently queried columns into your fact table. And what I mean by this is, a lot of times we'll end up having a dimension table and we join it to the fact table and we end up filtering on that dimension table primarily and using the join to filter on in our fact table. This is typically done sometimes with time dimension tables. And the reason it works in Redshift, the reason it doesn't perform as well is that we're not able to leverage the zone maps as effectively in your fact table and reduce the I/O in your fact table. So if there's a column that you're typically filtering on, materialize it into your fact table and filter on it there. It's a columnar data warehouse, so adding a couple extra columns isn't going to reduce performance. The next is calculated values. These are ones where maybe you have a where clause and you're wrapping a column in a function, you're extracting a value out, and then that's part of your where clause. If you can, instead take that value and extract it out and write it out into a column and actually query off that, and then the zone maps can actually be used. One that I do see that we sometimes end up unfortunately seeing in some customer clusters when I'm helping customers troubleshoot performance issues is temporal columns as a distribution key. So think of these as like dates, and maybe the number of months in a year is a really bad example it's a good example of how not to do this. But yeah, say you only have 12 values for the months of the year. That does not make a very good distribution key because there's only 12 unique values to distribute the data across the cluster. So as a rule of thumb, I usually just say simply avoid temporal values for distribution. Varchars, chars, numeric, they are data types where you can actually set the length of. Keep them as narrow as you can. Redshift does a great job. It will store them as efficiently if you declare it a varchar 1000 or a varchar 2. It's going to take up the same amount of space. However, there's a little bit of query overhead. We use up more memory in Redshift if you make those really large. So if you have, you're storing an abbreviation that's only a couple characters, don't declare it as a varchar 1000. Declare it, varchar 2 or 5 or 10 or something small, and you'll save memory in your Redshift cluster query execution time. The last two I did talk about. That was the analyze compression command. Definitely run that, and then also make sure sort keys are on the columns you primarily filter on. So let's move into data ingestion. So the first piece we're going to talk about is disks in Redshift. One thing that a lot of people don't realize is that the disks are actually much bigger than what we give you. They're actually 2.5 to 3 times the size. And that's because the advertised space that we put on the pricing pages and all that stuff is the space that you get to use to write your data. Obviously, we need a lot of other space. We store mere redundant copies of data, which I'll talk about in another slide. There's an operating system, there's scratch space, there's all sorts of stuff like that, and that's why the disks are significantly larger. The important thing is, I guess if you're comparing it maybe to an on-premise system and you have a data warehouse on site, that's why our disks might seem smaller than they are, but they actually are quite large. So moving on to data redundancy, which I've talked a little bit about or mentioned, we store 2 copies of the data in a Redshift cluster. We typically call this the local and the remote, but when a commit happens or finishes in Redshift, your data has been safely written to 2 of the compute nodes, with the exception of if you're using temporary tables. So temporary tables are very important to use because they write twice as fast because they're skipping that second copy. So if you are doing things that are scratch space in nature and you don't need to persist them, use a temporary table. They do write twice as fast. Also, we back data up asynchronously in Redshift. So this kicks off every 5 gigs of change data or 8 hours, whichever happens first. You can also take a backup at any time, a manual snapshot as well, which is a good thing to do if you're going to be making some drastic schema changes, for example. You can also disable backups, those backups to S3 on a specific table. There are some cases for that for transient tables that do need to be permanent and can't be temporary tables. So Redshift is an ACID compliant, it's fully transactional data warehouse. The isolation level we use in Redshift is serializable. You can try to change it, it'll say it did, but it won't. Every transaction is serializable in Redshift. There are 2 phases to our commit. There is a local commit, which happens at the slice level, and then there's a global commit that is basically the coordination of all the slices in the cluster to make sure that everything is finished. Commit statistics can sometimes be important to take a look at. This is a GitHub script for that. And that's because Redshift isn't a transactional database. It's meant for data warehousing, not high throughput of transactions. The one design consideration that I'll sometimes, or issue I'll see some customers kind of do is they'll have a workflow that's creating a ton of tables and maybe loading little things, and they don't wrap that workflow in a transaction. And what ends up happening is a lot of times you'll be running with implicit transactions turned on or something like that with your client tools, and you'll end up having a ton of transactions. And it's a really easy fix. Just wrap the workflow in a transaction. Chances are you probably want it in a transaction anyways, because if it fails halfway through, you don't want it half done. So pretty easy fix, and it's probably the right thing to do. So let's talk about how you actually get data into a Redshift cluster. The primary way of doing that is with the copy statement. The copy statement works primarily against S3. That's how most customers will load data. And in this example here, I have one of our dense compute 2 8XL clusters. It has 16 slices. and we have a single file. We'll just say that file is 1 gig file. And what would happen is if we executed a copy statement and loaded just that single file in a Redshift, what's going to end up happening is the first slice in the cluster is going to reach out, grab that file, download it, and it's going to parse it and do all the work it needs to do to get it to the rest of the slices. And it's not really going to run that fast. If, however, we took that same 1 gig file and we split it into 16 chunks, because we have 16 slices, what's going to happen here is this is going to run 16 times faster. And that's because every single slice in the cluster reached out to S3, all in parallel, because this is an MPP share nothing architecture. Everything works on everything. They're all going to download that. They're all going to parse it. They're all going to distribute it. And they're all going to write it across all the slices in the cluster. Our recommendation here on these files is ideally they should hopefully be 1 meg in size or larger, no larger than 1 gig after gzip compression. A few more best practices on copying data. I recommend using delimited files. Yes, we support Avro. Yes, we support JSON and fixed width format. Delimited files are easy to work with. They're also very fast in Redshift. They're pretty much the fastest file type we have to load. I always recommend picking a simple delimiter, pipe or comma or whatever, tabs. Don't pick some crazy UTF-8 character. Seen that happen. You can make it work, but it'll make your life a little bit more difficult. Pick a simple null character. Use a carriage return as your end-of-line character, things like that. Few copy options that if you haven't used Redshift before, and this is for the few of you that put up your hands, the max errors can be a useful option if you're just getting POC data in. It'll drop records. Except in varchars if you have invalid UTF-8 characters in your CSVs. So just a couple of handful of useful options. So what about with Spectrum? So Spectrum allows you to create an external table against S3. So you can query that external table with a select statement. You can also do an insert into and a select from those external tables. This, if you say have a data lake and you have files in your data lake, which will probably be in Parquet or ORC, you can load those directly into Redshift through Spectrum. Another cool thing you can do is you can aggregate data as it's coming in. You can select a subset of columns or transform the data with scalars and various other things. So you get a little bit more flexibility on the incoming data that's coming into your cluster if you use Spectrum. Another thing that Spectrum does is it also offloads some of the workload out of your Redshift cluster. So typically you want your cluster available for querying, servicing reports and such. If you use Spectrum for this, you have more resources available because that you're employing that second cluster. So Redshift is, it's petabyte scale data warehouse. It is designed for large writes. We talked about those 1 meg chunks, which I mentioned were immutable. If, for example, you come along and you write some insert statement, just a single line, and I do it all the time, I'll be in my client and I'll be writing test data in, and I add some row to a table, we don't ever want to fragment the blocks, those 1 meg chunks in Redshift. So what we actually do is we pick up the last block in each column, we clone it, we read it, we then stuff that new record into that block, we rewrite it back to disk, we throw away the last block that was at the end of the column, and that becomes the new block. If you think about it, that's a lot of work. Reading a 1 meg chunk and rewriting a 1 meg chunk for every single column in the cluster for that. That's just not, Redshift can do it, it will work, but it's not what it's optimized for. And that's why we'll sometimes say that a small write will cost roughly the same expense as writing 100,000 or more rows to Redshift. So Redshift really is designed around kind of batch bulk loading. Updates and deletes. A delete, we just mark the data as deleted. We don't actually delete it when you actually execute a delete statement. So that's why deletes kind of seem fast. That's also Redshift uses MVCC, which is multi-version concurrency control. And that's why if you have a transaction running, you will continue to see data exactly how it was when your transaction started. Updates are essentially just a delete and an insert in Redshift. So let's talk a little bit about a workflow that's very common. I get this is one of the most commonly asked things that I have customers ask me. So I really want to make sure to get this in here. And that's, how do you do an UPSERT in logic, in Redshift here? How does this logic work? So we have those 4 rows, same 4 rows we've been working all night. And we have a CSV table here, our CSV file sitting on S3, and we have these 4 rows in it, and we want to update that one, we want to update that one, and we have 2 more rows that we want to add to the end of the table. How do you do that in Redshift? So the workflow is we want to load that data, that CSV file, into a staging table, and then what we want to do is we want to delete from the production table all of the data that matches the staging table, and then what we're going to do is we're going to insert all of the data over into the production table. So how does that work? The first thing we're going to do is we're going to create a transaction. The reason why is we want to reduce the number of transactions in Redshift. We talked about that, but it is very important. The next is we're going to create the staging table, and it's going to be a temporary table. The next is the like clause, or the like statement or keyword, is going to pull over the distribution key from the production table to make the right copy faster from the one table to the other. It also has the consequence of pulling over, or the good consequence, it's not really a consequence, of getting the compression settings from the production table as well, which is really important. And that's because when we execute this copy statement and we load the data in, you'll notice I have comp update off there. What'll happen here is we're telling Redshift, hey, don't try and do the right thing in this particular case, which is figure out the compression for me. I know this, I don't want you to do that. And the reason why is typically this is going to be run repeatedly over and over again, maybe every 5-10 minutes. And we don't want to have Redshift figuring out the compression over and over again every 5 minutes on the exact same table. So that's why we copied it over. Then what we're going to do is we are going to delete from the deep dive table all of the rows that match that staging table. And then we can just safely insert all of the rows over, drop the staging table, and commit the transaction. So this is the best way to do this logic. So to kind of summarize the best practices on ELT, make sure you wrap your workflows all in a commit or a transaction, explicitly create a transaction. If you are going to be doing deletes, try to use drop tables or truncates instead. They won't leave behind kind of ghost rows, phantom rows, which need to be vacuumed up, which we'll talk about in the next slide. If you're using staging tables, which at some point I'm sure you will be, try to use a temporary table if you can. They write twice as fast. If you do need to use a permanent table, consider turning off backups so that the data is not being synced to S3. Keep the same disk keys on both tables for faster performance. The compression, setting the compression to off or making sure your table actually has compression settings baked in. The symptom you will see in your Redshift cluster if you are figuring out the compression over and over again, and I have a lot of customers who, I'll be talking to and they'll be like, yeah, my cluster runs at 80% CPU usage all the time. And it's because their cluster's figuring out compression for all these tables over and over again. That's the symptom you'll see is really high CPU usage that it doesn't really make sense. You just have a couple of copy statements running. And the last one, make sure you move all the rows over. We do also have a command called alter table append. It's essentially a move operation. It's a little known feature in Redshift. Not too many people know about it. And it essentially moves data from one table to another, it's a really good operation to use if you're moving large amounts of records. If you're not moving a large number of records, it's just like a small number, like low millions, just do an insert select. So let's talk about vacuum and analyze. Vacuum serves two functions in Redshift. One is to remove the ghost records or the deleted records out of Redshift. That's the first thing that it does. The second thing it also does is it globally sorts the table in Redshift. So when a copy or any insert select statement for that matter executes in Redshift and that batch of new rows comes in, we will sort that batch of incoming rows locally to that batch, and it's written to the end of the table. But that doesn't mean the table is globally sorted. So that's when vacuum needs to run. That's also why sometimes customers will their tables say that they're unsorted. If you have a single sort key and that happens to be a timestamp, for example, you probably don't need to run vacuum if you're loading data essentially in sorted order. And that's because we're locally sorting and the table kind of ends up being globally sorted as a result. The next piece is the analyze command, also very important. What that does is, or what it's for is it's for collecting statistics on the tables in your Redshift cluster. So this is for the query planner so it can pick optimal plans. I'd say most customers run vacuum and analyze nightly is kind of a typical thing. It really only needs to be run as frequently as it needs to be, but that is pretty common, especially if you have a little bit of downtime in the evening. Some customers only run it vacuum, particularly weekly, for example. And we do have a really good utility here on GitHub. A lot of customers take that utility. It's a Python script essentially, and it will vacuum and analyze your entire table. So that's usually what I recommend doing. Grab that utility and vacuum and analyze on some sort of cadence that makes sense. If you are changing and you have a table that's changing very frequently and maybe your query plans aren't always coming out the way you want, one thing that we will recommend is also to run the analyze command just on the columns that your predicates are on. So if you're filtering on a column, you can run analyze all the way down to just a subset of columns. And so some customers will end up recommending for them to put that into their load cycle. So if say you're loading on like a 5-minute cadence or something and the data is continually changing and thrashing about, run analyze after that load just on those columns. So let's move into node types, cluster sizing. We have two different node types in Redshift, our dense compute 2 and our dense storage 2. Technically, there was obviously a first generation of both of those, but we are on to the new generation of both of those. The main difference between these two platforms is one is solid state and one is magnetic disks. So they have obviously slightly different pricing profiles. The dense compute obviously perform quicker. And like I mentioned, the DC2 we actually just released like 2 months ago. So new platform. So cluster sizing. Production workloads should ideally be run on a multi-node cluster, 2 nodes or more. We do allow what we call single node clusters in Redshift. Those are fantastic for POC, playing around, dev work, QA work, all of that sort of stuff. I mean, I run a single node cluster myself, but if you have a production workload, use a multi-node cluster, and that's because you get that mirrored copy of the data for safety. The other thing is we give you the leader node at no additional cost. So as soon as you hit a 2-node cluster, you technically get a 3rd node for no extra cost. And that extra node actually does do some of the work. It does all that query coordinating and final aggregation and such. The other, I really hope that there's no one here that has this, but if you have a Redshift cluster that is still running an EC2 Classic, please move it out into a VPC. There is no downside to doing this. And we're typically seeing around a 2x across the board improvement on queries just by moving from EC2 Classic to VPC. One customer I had, they had a workload that was, it was their nightly ETL workload, and they called, and we're talking, and they were like, yeah, our nightly load is now a 17.5-hour nightly load, which was unacceptable to them because it was rolling into their daytime business hours and querying. And we looked at their cluster, and I was like, you know, you're running an EC2 Classic. Can you switch that to a VPC? And their just that change alone, their nightly load went from 17.5 hours down to 4. So if you happen to be a straggler running on EC2 Classic, definitely move to a VPC. Now, the sizing piece in Redshift, really how we recommend, or how every customer, when I first have a conversation with them, and they ask, how many nodes should I use? We look at how much data they have, usually uncompressed. We assume about a 3 times compression ratio. That's, you know, safe rule of thumb, or, you know, generalization if you're applying compression correctly. And we obviously, you know, usually customers will know, am I going to go solid state, am I going to go magnetic disk? And we size it for the amount of data that they have. You also want to, obviously, you want to maintain at least 20% of free space, or 2.5 to 3 times the size of the largest table in your cluster. So for example, if the largest table in the cluster is going to take up 10% of the cluster, you'd want to leave about 30% free space. And that's so that that table can be properly vacuumed. The next piece is the DC1 to DC2. Like I said, we just recently released DC2. DC2, most customers, especially if you're running on the 8XL, are seeing around a 2x performance increase. It's the same price as the DC1. So if you're not on RIs, you can move over very easily. You just do a simple resize. It's a few clicks in the console, move from DC1 to DC2, get the performance boost. There's no cost. If you have RIs, please contact us. We will work with you. There are things we can do if you are looking to maybe potentially migrate your RIs over from DC1 to DC2. It's not a straight over migration, but there are things that we can do. So, you know, reach out with me after the presentation or contact support. The last point is that Spectrum queries. If you are doing a POC and you're working with Spectrum, and this one kind of comes up a bit, is customers assume that, you know, Spectrum performance will be exactly the same on a single node cluster, a little tiny DC1 large, as it will be on a large cluster. It won't be. Performance in Spectrum scales depending on how large your Redshift cluster is. So we will provision up to 10 Spectrum nodes per slice in your Redshift cluster for each query. So there is a correlation between the performance you get in Spectrum and your Redshift cluster. So additional resources. I've talked lots about these GitHub scripts. All of this stuff is on GitHub. I'll just kind of walk through them quickly. The admin scripts, those are scripts that our solution architect team, the team that I'm on, our database engineering team, which is a part of the Redshift team, they're the ones that you may interact with. These are scripts that we've all found really useful when we're working with customers, diagnosing issues and that sort of thing, and we put all of those on GitHub. The same with the admin views. They're very similar to the admin scripts, but they end up being views. I've talked about the vacuum utility and the column encoding utility. Those are also, like I said, on GitHub. You saw the links earlier. So those, you'll find those there as well. Highly recommend checking those out. A couple of blog posts worth calling out. These are, I think, are kind of our three top blog posts. The top one there was written by one of our database engineers. It's a series of 5 blog posts that goes through table design and how a lot of like sort keys and distribution keys work. I highly recommend checking that one out. If you understand everything that he's written, you should be in good shape with Redshift. And then the top 10 performance tuning techniques was kind of, the theme for that was, what are the top 10 things that we see kind of customers get hung up on when configuring a Redshift cluster? So that one is totally worth checking out. And then the same kind of theme on the Spectrum one. I think we have about 10 minutes left, so we can do Q&A.